Good afternoon, my grade 11 math class. I am prepared to teach you a few things over the course of the next week using this video series. I'll put it on YouTube so that you can watch it again and again. And Mrs. Berg, while you are in class, you're welcome to turn it on and off if kids need or the students need to go over anything, or if it goes just a little too fast, feel free to stop and start. So we're going to skip the next unit that would follow in our book, in our workbook, and we're going to go on to this unit, which really does tie into the last one, which was about factoring. So what we're going to be doing, and as you read the front of the screen or in your book, it says that we are going to be doing some algebra, and we're going to be using rational expressions. So we know if we take 4 divided by 7, or 4/7, which is a fraction, and we know that the answer to a division question is a quotient, we end up with a rational number. So not a square root, but an actual rational number. We also know that the quotient of two polynomials meaning two terms, is also considered a rational expression. So a single variable rational expression is a fraction in is an algebraic fraction in one variable in which the numerator and the denominator are both polynomials. So what I'm talking about right now, and what this unit's going to be about, is rational expressions. There's something on the top and there's something on the bottom. Notice it can be a monomial or it can be a binomial on the bottom. So in this one, in this unit, we're going to learn how to subtract, add, multiply, divide, all of those things, and we're also going to learn to do some problem solving. So now we have just finished our factoring unit, so you can see that we're going to use the same method as we had in the past. We're going to find our greatest common factor. We have to remember our difference of squares, x squared minus 9, x plus 3, x minus 3, those kind of things. Factoring by inspection, so if I'm given something like this, I know that I can go directly to my factors. By decomposition, that's if I have a big number out front of my x, and then I multiply my last numbers together. And then the grouping, where I take my two terms at the front, two terms at the back, and try to find something common to both. Now, I'm going really fast because you have just finished this unit, so we don't need to worry about that at all. I'm just going to go on, and let's look at what we've got right now. Here we go. Oopsie, I have a double page here. So here we go. What we've got is we're going to investigate. By using rational expressions, we're going to create a table of values. So here's the rational expressions that we've been given. There's one here, and there's one here. And what we want to do is just substitute our value for x. We'll put in 0, we'll put in 1. We're just going to solve. Now when we do this, remember that my numerator has to be evaluated, my denominator has to be evaluated, and then I divide them out. So in the case of the first one, I'm just going to take this first expression, which is 2. I'm going to put a 0 in for my x, and I'm going to add it. Again on the bottom, I'm going to go 0, and I'm going to have that squared plus 3, 0, plus 2. Now, remember, I evaluate the top, that's 2. I evaluate the bottom, which is 2, and that gives me an answer of 1. We'll continue on down 1, 2, 3, and 4, but let's just have a look at this other expression. We have a 2 up on top, and we have an x plus 2. So I'm going to do the same thing. I'm going to put in some numbers. I'm going to put my 0 in for my x, and I end up with a 2 over 2, which equals 1. So we're just going to continue on and finish this up. So I don't need to talk it through. I'm just going to tell you that I'm going to add 1 each time wherever the x appears, and I will solve. And I should get 2/3. Now if I go and do the same thing on this side, remember there's a constant on top, so it's a 2, and if I put my 1 in for the x, I'm going to get, oh, what do you know, 2/3. Interesting. Let's put in the 2. 2 goes in for my x, plus 2. I put a 2 in here for my x. I'll put a 2 in for this x. And when I finish it up, I should get a 6 over 12, which equals 1/2. We'll simplify it. And then I'll find the same thing over here. We have a 2. I put in my 2 for my x plus 2 equals 2 over 4, which of course equals 1/2. Last couple. I simplify it the best I can and I get 2/5. And obviously you know the last one is going to work out to be the same. We'll just do that quickly. We'll just put in our 4. And you'll see, obviously, there's a reason we're doing this, and that is I am comparing these two expressions. So as we investigate, we find out that the one column will equal the other column, even though the expression appears to be a little different. So at this point, if you're done, we'll just continue on, and we can say that, what can we say about the values of the rational expression when we're replacing it with 0, 1, 2, 3, or 4? So no matter whether I was given this expression or this expression, they were both the same. They were equal. So just go ahead and write that in. So what we're saying is this expression that was in the first column and this expression that was in the second column are considered equivalent forms of the rational expression. To explain why they're equivalent, we're just going to go through and do a little bit of a procedure here to explain it. So why do we have what we have? The first thing it says, write the numerator 2x plus 2 and the denominator in a factored form. And then what we'll do is we'll reduce it by dividing out common factors, or meaning we can cancel our factors to show that this is indeed the same thing as this. So, as you know, first thing we need to do is find in our first expression what is the common factor. Oops, I highlighted the wrong one, but it's the same. There we go. And we pull out 2, and I'm left with x plus 1. Now, if I factor the bottom, I'm going to do the same thing. I'm going to end up with an x and an x as my first term. And then my last term is going to be a 2 and a 1. And when I add them together, I'm going to end up with a 3 in the middle. So this is just what we've been doing. Now, here's the new thing. I can cancel out factors. Notice in the brackets up above, I have an x plus 3. So here's, x plus 1. Here's the x plus 1. I also have an x plus 1 down below. Because of that, I can cancel these out. And what am I left with? Well, I'm left with a 2 over x plus 2. So once I factor, I can actually cancel out my factors as long as they're on the top and on the bottom. Notice then that expression that we started in the first column can also be written as it is in the second column. It's considered to be in lowest terms. Notice this was what I was left with right here. 2 over x plus 2 cannot be further reduced because the two 2's cannot be reduced because they are not equivalent. So what I want you to recognize is we can cancel out factors, but we can't cancel out just variables that are in the bottom and on the top. We must reduce fractions. We have to cancel factors, but not actual terms. So yes, I can cancel this out. That's okay, but I can't cancel this out. They are not the same. Good. All right, so let's continue on. We are going to now do the same kind of thing, same expression, but now we're going to put in some negative values and see what happens. And if you cannot work it through, it's going to be considered not defined. So the first thing we're going to do is put 0 in to the top. And I get a 0 in there, I get a 2 on the top. I'm taking out a step at this point. All I'm doing is I'm putting 0 in here, 0 in here, 0 in here, and I'm left with 2 over 2, which equals 1. Now over on this side, if I put a 0 in for the x, it's 2 over 2, which is also equal to 1. So easy. I'm not showing you all the steps as I did in the last page, but we know all I'm doing is substituting this 0 in for the x's. Now, if I do that for the -1, what I'm going to end up doing is I'm going to put a -1 in here, I put a -1 here, a -1 here. And when you do that, I'm going to end up with a 0 on top. But I'm also going to end up with a 0 on the bottom. You can go through and plug in those -1s, but that's exactly what we're going to end up getting. When we do that, we call this indeterminate. It's not just because 0 is on the bottom, but there's a 0 on top, and we call this expression indeterminate, meaning we really don't know much about it. All we can say is it's 0 divided by 0. This value, however, when I put my -1 in, and I will end up getting a 2 over 1, which equals 2. Again, feel free to go through and substitute these numbers in. When I take a -2 and I put it into this expression right up here, I end up with a -2, but this time my bottom will turn out to be a 0. When I have it divided by a 0, we all know we call that undefined. We cannot divide by a 0. If I go ahead and put the -2 in the top, in the next column, I will also get a 2 over 0, which is also undefined because we cannot divide by a 0. All right, and then the last one. If I put a -3 in there, and I'm going to leave you to do that, I will end up with an answer of -4 over 2, which equals -2. But on this side, when I put in my -3, I will end up with a 2 over -1, which works out to a -2. So, taking all that information that I've had, let's figure out for which values is this x undefined. And we know that it's when x equals -1. Notice, we're going to call it not defined or indeterminate. It doesn't really matter, but we're going to say that they're both -1 and -2. We ended up with words meaning that we can't do it. It won't work. In C part, which values are not defined? So I'm looking now at the last column. Which one was undefined? It was the one where x equals -2. Again, I'm looking at this one right here. Whereas in the first case, it was this one and this one. Now, finally, why do the values in B and C result in expressions not being defined? We know that it's division by 0 is not defined. We know that we can't divide by a 0. All right, so values of a variable which result in the value of a rational expression not being defined are called, we're going to call these non-permissible values. These values are known as the restrictions, and we've talked about this a little bit, but we're going to call these non-permissible, the ones where we end up getting a non-defined or undefined. Non-permissible values are values of the variable which make the denominator equal to 0. So why do we need to know that? Well, we need to figure out what things will not work and what values will work in our x. Note that although these are equivalent in the rational expression like we did on the page before, they do have different restrictions, as evidenced by up here on the top. We had, in this one, we only had the -2 undefined, and in here, in the first column, we had -1 and -2. So they have different restrictions, even though they are equivalent forms. So what does it say? The restrictions must be determined before dividing out common factors. So let's turn the page and let's have a look at what that looks like. We need to have it in simplest form if the numerator and denominator have no common factors other than 1. So what this means is this. I need to know what x cannot be. So we know that x cannot equal 0. There's my restriction. I also can cancel out a few things. Now, because this is a monomial, I can just do a simple cancellation. I end up with a 6 up on top and a 1 because 2 goes into both the top and the bottom. Notice the bottom also has an x and the top